Hello. In this video, we want to discuss group of automorphisms. Group of automorphisms of a given group. We will see some particular kind of automorphisms that we have already discussed, namely conjugations, and we call them inner automorphisms. We describe the group structure of inner automorphisms, and then we focus on the case when the group is a cyclic finite group of order n, and describe the automorphism group of cyclic groups of order n. Okay, let's again start with our meta example. So in our meta example, we started with symmetries of an object. Now, what happens if the given object is a group? Then in that case, symmetries of the group G consist of group isomorphisms from G to itself. A group isomorphism from G to itself is called an automorphism. This phrase automorphism is often used in algebra to describe isomorphisms from some algebraic structure to itself. So this auto tells us that I'm giving you a function from an algebraic structure to itself. And so an automorphism is always an isomorphism from some algebraic structure to itself. And these can be viewed as symmetries of the group G. The set of all the automorphisms is denoted by AUT of G, the group of automorphisms of G. And following the meta example that we had, the group of automorphisms of G and composition form a group. We have mentioned this, that in general, whatever object that I give you, the group of symmetries, the set of symmetries of that object forms a group under composition. So the set of symmetries of a group, which is precisely the set of automorphisms of G, under composition forms a group. You can check them, check all the properties of being a group one by one, and see that it is indeed a group. We have already mentioned that conjugation by an element is an automorphism of the group G. So if I give you an element small g, then C sub G is the following map from the group G to itself. C sub G of X is conjugation of X by G, which is Gx, G inverse. And we have discussed that this is indeed an isomorphism from G to itself, and that means that it is an automorphism of the group G. The set of all the automorphisms of the group G that are coming from conjugations is called the set of inner automorphisms. So again, the theorem that we are going to brief, we have seen some parts of this before, but I'm going to collect all these results related to conjugations in this theorem, says that if I start by an element, small g of the group capital G, then conjugation by G, if I denote conjugation by G by C sub G, and that means C sub G of X is defined to be X times X, G times X times G inverse, then C sub G is an automorphism of the group, and we call it an inner automorphism. And moreover, the function that sends an element G to C sub G from the group G itself to the group of automorphisms of G is a group homomorphism. So this function C that sends the element small g to the conjugation by G is a group homomorphism, and moreover, the kernel of this group homomorphism is precisely the center of the group G. And as I've mentioned it earlier, the image of C consists of inner automorphisms, all the inner automorphisms of G, and it is denoted by I and N of G, so that this abbreviates inner, so the image of this function C is the set of all inner automorphisms of G. Now, the image of this group homomorphism is the set of inner automorphisms, and the kernel of this group homomorphism is center of G. Therefore, by the first isomorphism theorem, I can deduce that the group of inner automorphisms so we can deduce that the group of inner automorphisms is isomorphic to G modeled by the center of the group G. Moreover, the group of inner automorphisms is a normal subgroup of the full group of automorphisms of G. So the full group of automorphisms of G has this normal subgroup, which consists of inner automorphisms. So far, we are describing part of the full automorphism that we call the inner automorphisms, and the inner automorphisms is isomorphic to the quotient of G by its center. Of course, when G is abelian, then G is the same as its center, and there is no inner automorphism. There is no non-trivial inner automorphism. So in that case, the group of inner automorphism, it doesn't give us any interesting automorphisms of the group G. But when G is not abelian, in that case, center of G is actually a proper subgroup, is strictly smaller than G. In that case, we are getting some non-trivial automorphism of the group G. Okay, so we have already discussed that conjugation by G is an automorphism of G. So we are going to start by proving the part B of this theorem, and then we get to this part. As I've explained, this part is a consequence of the first isomorphism theorem. But let's go through the details of the arguments and see how they go. So again, let's quickly also show why C sub G is a group homomorphism. Well, that means I need to show that C sub G of X times C sub G of Y, conjugation of X times conjugation of Y, both of them by G, is conjugation of X times Y by G. So that is what we want to show. Let's do the computations. So conjugation of X by G is G times X times G inverse. Conjugation of Y by G is G times Y times G inverse. And remember, because multiplication is associative, I don't need to write down parentheses and say in what order I'm going to multiply these terms. In particular, I can multiply these two terms first and then follow it up by other multiplications. But notice that the product of these two elements is simply the neutral element of the group. And when I multiply the neutral element, E sub G, by X, I'm going to get X back. And therefore, this whole product, so I can get rid of this completely. I can drop it out, and I end up getting that it is G times X times Y times G inverse. And that means that I end up getting conjugation of XY by G, and that's exactly what I was looking for. So that shows that C sub G is indeed a group homomorphism. Now, why is it invertible? To show that it is invertible, we actually kind of check that this function C is a group homomorphism, but a particular case of it. So if we knew that this function C is a group homomorphism, then that would have implied that CG composed with CG inverse is identity, C of the neutral element, which is identity. So if we knew that C is a group homomorphism, we could have concluded that this is identity. And similarly from the other way. And that means C sub G inverse should be the inverse of C sub G. From this argument, this is a suggestion on what the inverse of C sub G should be. As soon as we understand that C sub G is invertible, we can deduce that it is an automorphism, because we already know that it's a group homomorphism. So it's enough to show that it is a bijection to deduce that it is a group of automorphism. Okay, so now we take this suggestion and try to show that C sub G inverse is the inverse of C sub G. Okay, so that is what I want to do. Now that I know what I'm looking for, the proof should not be that hard. So what does that mean? So I want to show that C sub G inverse is the inverse of C sub G, and that means as two functions. So that means that when I look at the composite of these two functions, I'm supposed to end up getting the identity function. That means that this composite is supposed to send x to itself. Let's see where x is mapped to under this function. So when I feed it x, it's composite of two functions. So this means first I need to conjugate it by G inverse and then conjugate it by G. But remember, conjugation by G inverse means that I need to multiply x from left by G inverse, from right by inverse of G inverse. I can simply write down G or do it in two steps and say that it is inverse of G inverse. And then I need to conjugate whatever I get out of this conjugation by G. That means I need to multiply this from left by G and from right by G inverse. Now again, multiplication is associative, so I can do these multiplications in whatever order I'd like. In particular, I see that this G and G inverse are close to each other, so I start multiplying those two, essentially canceling them out. These two terms cancel each other out, and this is essentially G, so then I get G times G inverse, and these terms cancel each other out. I end up getting simply X, and that's exactly what we were looking for. We end up showing that composite of these two functions is the identity function. This is true for every G, in particular it is true for G inverse. So as I plug in G inverse, I get that C of G inverse composed with C of inverse of G inverse, but inverse of G inverse is simply G. So this is simply G. So I end up getting that composite of C sub G inverse and C sub G is identity as well. Now, composite of C sub G and C sub G inverse, we already discussed it is identity. So composite of these two functions, no matter what order we pick, is the identity, and that means that these two functions are inverse of each other. And therefore, conjugation by G is an invertible function. It's an invertible group homomorphism, and so it is an automorphism of the group G. So we showed that conjugation by G is an automorphism of the group G. Now let's see why the function C is a group homomorphism. Recall that the function C, when I feed it an element of the group, it gives me the conjugation by the element G. So this way we are getting an element of the group of automorphisms of the group G. So we want to say that this function C is a group homomorphism. That means we have to show that conjugation by G1 times G2 is the composite of conjugation by G1 and conjugation by G2. So I want to show equality of these two automorphisms. So I'm thinking about them as functions on the group G, and I want to see why these two functions are equal. So I'm going to apply these functions to an arbitrary element x of the group G and see if I end up getting the same element of the group. Okay, so let's start with composite of these conjugations and see what we end up getting. So when I apply composite of conjugation by G1 and conjugation by G2 to the element X, I need to start with conjugating by the element G2 and then conjugating by the element G1. Let's start conjugating it by G sub 2. That means I am going to multiply X from left by G sub 2 and from right by inverse of G sub 2. Then whatever this product is, whatever this conjugation is, I'm going to conjugate it again, this time by G sub 1. That means I'm going to multiply it from left by G sub 1 and from right by G sub 1 inverse. As always, because multiplication is associative, I am allowed to choose whatever order of multiplication I'd like. I'm going to group G1 and G2 together. And notice that as I group G2 inverse by G1 inverse, this product is nothing but inverse of G1 times G2. Remember, when we want to find inverse of product of two elements, it is in product of inverses, but in reverse order. So G1 times G2, the whole thing inverse is G2 inverse times G1 inverse. So this part we did not touch, and this part is precisely inverse of G1 times G2. That means the whole thing is conjugation of X by the element G1 times G2. So it's conjugation of X by G1 times G2, and that's exactly the equality we were looking for. So this implies that the composite of these two conjugations is equal to this conjugation. That means the function C is a group homomorphism, as we claimed. Now, what is kernel of this group homomorphism? So suppose G is in the kernel of this group homomorphism. What does that mean? It means G is sent to the identity, to the neutral element of the group of automorphisms of G. But the neutral element of the group of automorphisms of G is the identity function. So C sub G, conjugation by G, is supposed to be the identity function. So let's apply conjugation by G to an arbitrary element X. Because this is supposed to be identity function, we deduce that no matter what X is, C sub G of X, conjugation of X by G, is supposed to be X. So no matter what X is, G times X times G inverse is X. Now multiplying both sides of this equation by G from right, I end up getting, so when I multiply by G, this cancels out, and I end up getting that G times X is equal to X times G for every element of the group. That's precisely the definition of being in the center. That means that G belongs to the center of the group. And I can go the converse as well. I mean, all these statements are if and only if statements. So altogether, we deduce that an element belongs to the kernel precisely when it belongs to the center, and that means kernel is equal to the center, which completes proof of the part B. Now, by the first isomorphism theorem, we know that if I give you a group homomorphism from G to some other group, then G modeled by the kernel of this group homomorphism is isomorphic to the image of this group homomorphism. Now, kernel of C, as we just proved, is equal to the center of the group. And image of C, by definition, consists of all the inner automorphisms, and the set of all inner automorphisms is denoted by I sub n of G. So image of C is the set of all inner automorphisms of the group G. Therefore, by the first isomorphism theorem, we deduce that the quotient group of G by its center is isomorphic to the group of inner automorphisms of the group G. In particular, the set of all inner automorphisms is indeed a subgroup of the group of automorphisms of G. Now, we want to show that this subgroup is indeed a normal subgroup. In order to show a subgroup is a normal subgroup, so the definition that we gave was that N is a normal subgroup of G if and only if every left coset that's represented by G, that's a right coset, is equal to its left coset. But we also discussed that this is equivalent to saying that N is invariant under conjugations. That means G times N times G inverse is equal to N. We are not saying that when I conjugate it, every single element is mapped to itself, but we are saying that if I start with some element of the subgroup N, when I conjugate it, I end up getting another element, possibly different element of the group N. But I will be still inside the group N. In that case, if this is the case for every G, then N is a normal subgroup. So a subgroup is a normal subgroup if we say it like this: if it is invariant under inner automorphisms. So if every single inner automorphism sends it to itself, then we call it a normal subgroup. Now, we are going to use this condition in order to show that the group of inner automorphisms is a normal subgroup of the group of automorphisms of G. Okay, so that means what? That means I'm going to start with an element of this, which is a conjugation by some element, and I'm going to pick some element of automorphisms of G, and then I'm going to conjugate this conjugation by G itself, and I want to show that this composite itself is an inner automorphism. So we need to show that this, we know, is composite of 3 automorphisms of the group G, and therefore it is an automorphism of the group G. We want to show it's not an arbitrary automorphism, but rather it is an inner automorphism. Remember, an automorphism is called an inner automorphism if it is conjugation by some element of the group G. So I need to apply this function, I need to apply this automorphism to an arbitrary element of the group G, let's call it X, and I need to check whether or not I am getting conjugation by some element of the group. Okay, so let's apply this automorphism to some element X and see what the result is. So again, it's composite of 3 group homomorphisms. I'm going to apply them one after another. Let's start with F inverse. We apply F inverse to X, and then I need to conjugate this element by G. So C sub G of this element means multiplying this element from left by G and from right by G inverse. Now I'm going to apply F to this function, and remember that F is a group homomorphism, and therefore it preserves multiplication, and I can switch the order of taking inverse. That means this whole thing is equal to F of the first term, F of the second term, and F of G inverse. It's F of G, F of the second term, and F of G inverse, and I need to multiply them one after another. Now notice, by definition, F of F inverse is identity, so in the middle I only get X, I'm not touching the first term. And at last I get again fg inverse, which means I'm conjugating x by f of g. So it's c sub f of g of x. This equality holds for every x inside the group. And that means this conjugation that I was interested in is equal to the group automorphism, the inner group automorphism conjugation by f of g. In particular, this is an inner automorphism. So I started with an arbitrary inner automorphism. I looked at its conjugate under some element of the group of automorphisms of G, and I showed that we end up getting another inner automorphism of the group. So this means when I conjugate the group of inner automorphisms by F, I end up getting a subgroup of inner automorphisms of G. But notice that this is true for every F, not just one, but every F satisfies this property. And indeed, this is enough to show that it is a normal subgroup. And how does the argument go? The point is that this statement is true for every F. In particular, it is true for F inverse. So instead of F, I can write down F inverse, and then inverse of F inverse is simply F. So because this is true for every F, I can apply it for F inverse. I end up getting that F inverse inner automorphisms of F composed with F is still a subset of inner automorphisms. Now I can apply F to both sides of this from left and F inverse from right. Then in this side, I end up getting F cancels this out, F inverse cancels this out, I end up getting inner automorphism of G, and in the other side, I end up getting conjugation of that set. Now notice we have that this conjugation is a subset of inner automorphisms. Now we showed inner automorphisms is a subset of this conjugation, therefore they are equal. That's exactly what we were looking for. So we end up getting that when I conjugate the group of inner automorphisms by F, by some automorphism of the G, of the group G, I end up getting the entire the set of the set that contains all the inner automorphisms. This is true for every automorphism of the group G, and therefore that means that the subgroup of inner automorphisms is a normal subgroup of the full group of automorphisms of G. Again, let me point out that if you look at this argument, we see that if for every G in the group G, Gn G inverse is a subset of N, and N is a subgroup of G, then N is a normal subgroup of G. I don't need to start with equality. I can deduce the inequality out of this, and the reason that we can do it is because we have the same result for G inverse, because this is supposed to be true for every G. And then from here, I can deduce the other side of this inequality, this inclusion. So I can use these two to deduce equality, to deduce that every conjugation sends N to itself, and therefore it's a normal subgroup of the group G. This is what we essentially proved within the proof of this theorem. Okay, let's see some examples. As I have mentioned earlier, when G is abelian, then the group of inner automorphisms consists of only one element, and that's the identity. Why is that the case? Because when G is abelian, G is equal to its center, and therefore center is in the kernel of the kernel of the is equal to the kernel of the group homomorphism C. In particular, the entire G is a subset of the kernel, is equal to the kernel, and that means that C sub G is identity for every element of the group. which means the only element in the inner automorphism, in the group of inner automorphisms, is the identity. Now let's look at the opposite of this. What do I mean by that? So in the example, that if we start with the symmetric group, then the group of inner automorphisms is isomorphic to the symmetric group if n is at least 3. The group of inner automorphisms of S sub n is isomorphic to S sub n if n is at least 3. Okay, why is that the case? We have already proved that the group of inner automorphisms of G is isomorphic to the quotient group of G by its center. And therefore, the group of inner automorphisms of the symmetric group is isomorphic to the quotient of symmetric group by its center. But remember, we have proved that if n is at least 3, then its center is trivial. That's the phrase that we use if the center has only the neutral element as its element. It has only one element, and that is the neutral element. That is what we proved for symmetric groups that has S sub n when n is at least 3. Therefore, this is only identity. It has only one element. And now notice that, so this means we deduce that the group of inner automorphisms of S sub n is isomorphic to S sub n mod out by the trivial subgroup. But modding out by trivial subgroup doesn't change the structure of the group. You simply take the quotient, you simply take this map, you send the coset of the trivial subgroup that's represented by x to x. Then it's clearly a group homomorphism. And because this set has only one element, and that is x, I'm sending that element to itself. So it is only bijection. I mean, it is injective and it is surjective. I'm capturing everything. So it is an isomorphism. And that means that this quotient is isomorphic to G, and therefore this quotient is isomorphic to S sub n, which means the group of inner automorphisms is isomorphic to S sub n when n is at least 3. Okay, so now we've seen the two sides of inner automorphisms. When G is abelian, there is no non-trivial inner automorphism, but in some cases, when the center is trivial, then every element of the group gives us a different automorphism of the group simply by conjugating using that element. But do we have really other automorphisms? Are there some automorphisms that are not inner? So if I want to see new automorphisms, it would be easier to find these new automorphisms in the abelian setting, because in this setting, there is no non-trivial inner automorphisms. Any automorphism of any non-trivial automorphism of an abelian group is already an automorphism that's not an inner automorphism. So we are going to look at a cyclic group of order n, and we are going to describe its group of automorphisms completely. Okay, but let's start with introducing a notation. So we are going to denote a cyclic group of order n by C sub n. So C sub n denotes a cyclic group of order n. Suppose elements of C sub n are different powers of the element G, the generator G. So C sub n is generated by the element small g, and it has n elements. Therefore, the set of elements consists of the neutral element g, g squared, and so on till we get to g2 power n minus 1. So this is a cyclic group of order n. And the theorem that we are going to prove is that the group of automorphisms of a cyclic group of order n is isomorphic to the group of units of the integers modulo n. Okay. We are going to show two lemmas before we get to the proof of this important theorem. This theorem will be used later in field theory if you study cyclotomic extensions. Okay, so let's see how we can prove this. We are going to show two lemmas in order to, before we get to the proof of this theorem. Let's start with the following. If I give you cyclic groups, C sub n, then for every integer, you can give me a group homomorphism from C sub n to C sub n, which simply raises an element x to power k. In fact, f sub k, by the same rule, is a group homomorphism as long as the group that I'm working with is an abelian group. Now, moreover, these group homomorphisms that I get out of f sub k's, they are going to be the same functions if the index mod n are the same. So if the residue class of k1 modulo n is the same as the residue class of k2 modulo n, then the function we get out of this rule are the same if I use k1 or if I use k sub 2. So these f sub k's depend only on the residue class of k modulo n and not on k itself, even though in the formula that I'm giving you, I'm using k, but it genuinely depends only on the residue class of k modulo n, and it does not depend on k itself. We'll come back to this in part, later when we want to prove the mentioned theorem. Now, so this f sub k, so here I'm not discussing the group structure, I'm just saying that the functions are the same, but no matter what k is, f sub k is definitely a group homomorphism. This is what I mentioned earlier, that this statement is true not only for C sub n, but also for every abelian group. And the last part plays an important role for us. It says that if the residue class of k modulo n is a unit in the set of integers, in the group of integers modulo n, then f sub k is an automorphism of the cyclic group of order n. And this statement, the last part, is in fact an if and only if statement, but this is the only direction that I'm discussing in this lemma. Okay, so let's start by showing why f sub k1 is equal to f sub k2 if k1 and k2 are the same modulo n. Okay, so let's assume that the residue class of k1 mod n is the same as the residue class of k2 mod n, and that's the same as saying k1 is congruent to k2 modulo n. And that means k2 is simply k1 plus an integer multiple of n. For some L inside Z, integer multiple of n. Now, I want to show that f sub k2 is equal to f sub k1 as two functions. So I'm going to apply both sides to x and see whether or not I end up getting the same values. Let's apply it to x. By definition, this is x raised to power k sub 2. But remember, k sub 2 is k sub 1 plus this integer multiple of n. So x to power k sub 2 is x to power k sub 1 plus an L. And this is equal to x to power k sub 1 times x to power n L. And that is x to the n raised to power L. Now, here is an important fact. For every element of the cyclic group of order n, x to the n is the identity. In order to show it, either we can use Lagrange's theorem Or we can point out that order of every element of a cyclic group of order n divides n, and therefore x to the n is identity no matter what x we pick. But let's use Lagrange's theorem. That's cleaner. So by Lagrange's theorem, we know that for every finite group G, x to power cardinality of G or order of G is the neutral element of G for every x in a finite group G. We proved this using Lagrange's theorem, which says cardinality of every subgroup divides cardinality of the ambient group. Using that, we deduced that order of every element of a finite group divides cardinality of that group, and from which we can deduce that x raised to power the cardinality of the group G is equal to the neutral element. So altogether, we deduce that no matter what x we pick from this cyclic group of order n, x to the n is the neutral element of the group, and therefore x to the n raised to the L is still the neutral element, and I can ignore this term completely. So I end up getting that it is equal to x to power k sub 1, and as I've explained, I can drop this out. I end up getting x to power k sub 1, which is simply f sub k sub 1 applied to x. This is true for every x, and that means this function is equal to this one. That's exactly what we wanted to show. So f sub k depends only on the residue class of k modulo n. Now I want to show part B. That means I need to discuss why f sub k is a group homomorphism. So I'm going to apply f sub k to product of two elements, x times y. By definition, that means I need to look at xy, raise it to power k. But remember, that means xy times xy times xy, k times. Now, because every cyclic group is abelian, I'm allowed to permute terms of this multiplication and put them in whatever ordering I'd like. In particular, I'm going to write down all the x's first and then all the y's. I'm going to get kx's, and therefore I get x to the k, and I'm going to get ky's, and that means y to the k. Of course, under the assumption that k is a positive integer. If k is negative, I don't write this equality, but rather I write inverses and then negative k of them. But in any case, when the group G is abelian, I have this nice equality that xy raised to the k is x to the k times y to the k, and therefore f sub k of xy is equal to f sub k of x times f sub k of y, which means f sub k is a group homomorphism. Now, I want to discuss this third part, and that means I want to show that f sub k is not only a group homomorphism, but it is also a bijection if the residue class of k mod n is a unit in the group of integers modulo n. It has multiplicative inverse in the set of integers modulo n. Okay, so in order to show that it is bijection, I'm going to start discussing why it is injective. You've seen it that a function, a group homomorphism, is injective precisely when its kernel is trivial. So I'm going to discuss and I'm going to understand the kernel of f sub k. So suppose x belongs to the kernel of f sub k. By definition, that means x to the k is the neutral element of G. But we know for a finite order element x, x to the k is the identity with the neutral element precisely when the order of x divides this integer k. Now, by Lagrange's theorem, as we have discussed, for every element of the cyclic group of order n, order of x divides cardinality of the group, which means O divides n. Now, if I tell you, and so in particular I deduce that order of x should divide both these two, so it's a common divisor of k and n, and therefore it should divide the greatest common divisor of n and k. Now, if I tell you that the residue class of k mod n is invertible in the group of integers modulo n, we know that that means the GCD of k and n is 1. But order of such element that was in the kernel was supposed to be a positive divisor of the GCD. But the GCD is now turns out to be 1. So therefore, order of x has to be 1. So if x is inside kernel of f sub k and k mod n has an inverse, then order of x is 1, which means kernel of f sub k has only one element if k has an inverse mod n. Now again, in your homework assignment, you've seen that if kernel of a group homomorphism consists of only the neutral element, then it is injective, but because it's an important result, I am going to go over this and over the proof of this statement. So I want to show that if I give you a group homomorphism, then it is injective precisely when, if and only if, kernel of f consists of only the trivial element, the neutral element. So let's assume that it is injective, and I want to deduce this statement first. So because f is injective, so I'm going to assume this, and I want to show that kernel of f has only neutral element in it. Of course, neutral element does belong to every subgroup, and in particular, it does belong to kernel of f. Now, if x is inside kernel of f, by definition, f of x is the neutral element of H. But neutral element of H is what neutral element of domain is sent to, because f is a group homomorphism. Now, f of x is equal to f of neutral element. Because f is injective, we deduce that x is equal to E sub g, and that's exactly what we wanted to show. Now let's assume that, so this implication means that the only element of kernel is the neutral element, and therefore kernel of f is equal to the neutral element. Now suppose kernel of f has only one element, and that is the neutral. I want to show that f is injective. That means I start with the assumption that f of x1 is equal to f of x2, and I want to show that x1 is equal to x2, and that is a question mark that I need to remove. Why do we have that x1 is equal to x2, assuming that f of x1 is equal to f of x2? Knowing that f of x1 is equal to f of x2 and multiplying both sides by inverse of this side, I end up getting that f of x2 inverse multiplied by f of x1 is equal to the neutral element of H. But remember, f is a group homomorphism, and therefore this side is equal to f of G2 inverse times x1. And f of this element turns out to be the neutral element of the codomain. But that means this element, x1, x2 inverse times x1, is in the kernel of f. So this is in the kernel of f. But what do we know about kernel of f? we know that kernel of f has only one element, and that is the identity, the neutral element. So this needs to be the neutral element. Now multiplying both sides by x sub 2 from left, we end up getting the desired equality. Now, going back to the proof of f sub k is inside the automorphisms of the cyclic group if the residue class of k mod n is an integer. If there is has an inverse in the group of integers modulo n. Okay, so we have proved that the kernel of f sub k is has only one element if the residue class of k mod n is invertible. Now, that means this function, we proved that because this is a group homomorphism and kernel has only one element, we deduce that this group homomorphism is injective. But now domain and codomain have the same number of elements, and that is n. Knowing that it is injective, I deduce that image of this group, this function, this group homomorphism, image of f sub k has the same order, has the same cardinality as the codomain, as the domain of f sub k, which means image of f sub k has n elements. But the codomain has n elements as well. That means image of f sub k is the entire codomain. That means f sub k is surjective. So it is injective, it is surjective, and it's a group homomorphism. So altogether we deduce that f sub k is in the group of automorphisms of the cyclic group C sub n. Now I want to show that that's it. That's the entire set of automorphisms of C sub n. Which means I'm going to show that if I start with an arbitrary automorphism of C sub n, it is of the form f sub k for some k, so that the residue class of k mod n has an inverse in the set of integers modulo n. So I give you an arbitrary automorphism of the cyclic group of order n, and I want to find a residue class of k, a residue class modulo n that is invertible, and f is equal to f sub k. Okay, that's my goal. Let's start with applying this automorphism to G. When I apply it, I'm supposed to get another element of C sub n, which means f of g is definitely of the form g raised to power k for some integer k that gives us these elements. That means k is definitely non-negative, and it is at most n minus 1. We can choose it like that. Now we have proved that an isomorphism never changes order of elements. Knowing that f is an automorphism, therefore it's an isomorphism, we deduce that order of f of g is equal to order of the element that we started with, and that is g. But remember, g generates this group, and this group has n elements, and therefore order of g is precisely n. That means order of f of g is precisely n. But on the other hand, f of g is g to the k, and order of g to the k, so this means that order of g to the k needs to be n. But order of g to the k can be computed in terms of order of g. We know that order of g to the k is equal to order of g divided by GCD of order of g and k. This is a result that we have proved earlier. Now, in particular, knowing that order of g is n, we deduce that order of g to the k is n over GCD of n and k. Now, that means, this equality means that order of g to the k is n precisely when GCD of n and k is 1. Okay, so that means that k, the residue class of k mod n is actually is invertible in the group of in the integers modulo n. So not only this, but we also see that if I apply f to an arbitrary element of this cyclic group, that means something like g to the m, then because f is a group homomorphism, no matter what integer value m has, f of g to the m is equal to f of g raised to the power m. But f of g, the way that we have defined it, is g to the k. So this is going to be g to the k raised to power m. And now I can write it as g to power mk and flip m and k. So this is equal to g to the m and then raised to power k. And remember, this is precisely f sub k of g to the m. So this means what? This means this group of this automorphism of the cyclic group G applied to an arbitrary element of the cyclic group generated by G gives us the same thing as we apply the automorphism f sub k. That means this function f, this homomorphism f, this automorphism f is equal to the inner automorphism of to the automorphism given by f sub k, not inner, but rather the f sub k is the map that sends x to the k. So this observation implies that every automorphism is equal to f sub k for some integer k. Okay, now let's go back to the proof of the theorem that the group of automorphisms of a cyclic group of order n is isomorphic to the group of units of z sub n. I'm going to give you a function from z sub n cross to automorphisms of c sub n. We are going to check why it is surjective. We will show why it is a group homomorphism, and then we discuss why it is injective, and altogether we get the desired isomorphism. Okay, so theta, what is theta? I give you a unit from the ring of from the set of integers modulo n, and then I'm going to look at this residue class, and I give you f sub k. A priori, you might say, what happened? So doesn't this depend on choice of k? Or how do we know that it depends only on the residue class of k modulo n? But remember, we have already discussed this type of thing in the previous lemma. It's over here. So here we showed that if I tell you these two residue classes mod n are equal, you can deduce that f sub k1 is equal to f sub k2. So in particular, we get that the function we have defined only depends on the residue class of k mod n. We also discussed that this is an automorphism, is in the automorphisms of C sub n. So that's another reason. I mean, that's also another part of the argument that shows that the function that we gave here is indeed well defined. Let's see where it is. It's over here, yeah. So we deduce that this function that we have defined, so we show that if these two residue classes are equal, then f sub k1 is equal to f sub k2. We have also discussed that f sub k is indeed an element of the group of automorphisms of C sub n, and these two together imply that the function that we have is well defined. Now, in the previous lemma, we showed that every element of the automorphism group of C sub n is of the form f sub k for some k, which means theta is surjective. So far we discussed why we have this surjective map from Z sub n cross to the group of automorphisms of C sub n. Next, I'm going to discuss why this theta is a group homomorphism. So I'm going to feed it the product of two residue classes, and then I ask myself whether or not I end up getting composite of the following functions: theta applied to the residue class of K mod n, and theta applied to the residue class of L mod n. So this is F sub L, this is F sub K, and we want to show that this composite if F sub KL. And these are group homomorphisms, in fact automorphisms, of the cyclic group C sub n. And so it's enough to understand what they do to the element of this cyclic group. So again, we have to show why composite of F sub k and F sub L is F sub KL. Okay, so this is the equality that we want to show. So these are automorphisms from C sub n to itself. So I'm going to I'm going to apply these functions to an arbitrary element of the group C sub n, and I ask myself whether or not I end up getting the same value, the same thing. So applying this side to x, I need to first apply f sub l and then f sub k. As we apply f sub l, we get x to the l, but f sub k is a group homomorphism, so when I apply to x to the l, we get, so in fact here I don't need to use the fact that it's a group homomorphism, I can simply use the definition of f sub k, and that means that I need to raise this guy to power k. And that is x to power k times l. And that means I'm raising x to power kl, and that's exactly the equality we were looking for. So theta is a group homomorphism. Now, why is it injective? Again, let's recall that a group homomorphism is injective precisely when its kernel is trivial. So in order to show that theta is injective, it's enough to discuss why its kernel has only the neutral element. So suppose residue class of K mod n belongs to the kernel of theta. By definition, that means f sub k is identity, and that means when I apply f sub k to the generator of the subgroup G, I end up getting G. F sub k is g raised to power k, and that's supposed to be g. Multiplying both sides by inverse of g, this equality is equivalent to saying that g raised to power k minus 1 is the neutral element of the group G. And this type of equality are true precisely when the power is a multiple of the order of G. So knowing that g raised to power k minus 1 is equal to the neutral element, we can deduce that order of g divides k minus 1. And order of g is the generator of the cyclic group with n elements. So order of g is n, and n needs to divide k minus 1, which means k is 1 mod n. That means the residue class of k mod n is equal to the residue class of 1 mod n, and that's precisely what we wanted to show. We wanted to say that the only element in the kernel of theta is the residue class of 1 mod n, and that is what we showed, that if this residue class is in the kernel of theta, then it is equal to the residue class of 1. So it is injective. We have discussed that it is also surjective in the previous lemma. it is surjective, it is injective, and it is a group homomorphism. And altogether, we deduce that theta is an isomorphism from the group of units of integers mod n to the group of automorphisms of a cyclic group of order n. For now.